good morning, or good afternoon, as the case may be. Thank you for joining me today. My name is Dave Kempisty. I work at Evoqua Water Technologies. I'm the Senior Business Development Manager for Emerging Contaminants. And my juvenile joke that I lead off with is how do you spell emerging contaminants? And that's PFAS, as that seems to be the majority of my attention, and that's where my talk will focus today. So again, thanks for joining me, and look forward to walking through this slide deck. I think I have about 25 slides or so. I'm going to be talking about commercial technology applications for the removal of PFAS from water. And just to give you the punchline up front, I'm looking across different technologies, and there is no one panacea. There is not a destructive technology that can work in all applications. There is not an adsorption technology like ion exchange resin that is better in all instances than granular activated carbon, nor is granular activated carbon the preferred methodology. It all depends upon the particular treatment objectives and the solution that the customer is looking for, and site constraints and a variety of other factors that need to be considered. So the point I'm trying to make is that there is a comprehensive solution that should be analyzed and looked at in its entirety before just going with a scripted response. Here's an overview slide. I'll give the obligatory Evoqua Water Technologies slide, who we are, and then we'll get right into the solutions and capabilities for the removal of PFAS from water, groundwater, and cover a couple of different case studies. And then finally, I will end with some action steps that might be appropriate to consider. Evoqua Water Technologies, we're a leading provider of water and wastewater treatment solutions. So we offer a broad portfolio of different products. Here are our core commitments, and these are our core commitments that we make to ourselves, and these are our core commitments that we make to our customers as well. You can see our purpose, our vision, and our values listed on this slide. Transforming water and enriching lives, or enriching life. Water plays an instrumental role in our everyday lives, so much more than just drinking water. And because water is everywhere, so are we. Our vision, the world's first choice for water solutions. It's a critical and it's a finite resource, and we want to treat it accordingly and understand how to provide treatment aspects to any operation, more so than just drinking water. When I first came on board, I was thinking things in terms of drinking water or remediation aspects, and we certainly do that, but we play a much larger role in the water world as well. I mean, we're involved with everything from mining and manufacturing operations to paper and pulp processes to food and beverages and pharmaceuticals and microelectronics, as well as the aforementioned drinking water and remediation, wastewater, of course. And then I'd like to draw your attention to one particular value, the sustainable aspect of our operations, and we measure things in regards to our footprint and our handprint, with the footprint being our impact on the environment from Evoqua operations, but the handprint is taking a deeper look at how our teaming with Evoqua can change or positively affect the sustainability metrics of our customers. And so more of a comprehensive life cycle analysis of the offerings that we offer, again, to our customers. So no PFAS 101 slide, but I do have the PFAS tree on here and another juvenile pun that we will just touch on this briefly, and then we will leave it. And then I've got a couple of books that I wanted to make mention of here. I was the lead editor on both of these texts, and they talk about PFAS across the spectrum of challenges in this dynamic space. And so you can look at those challenges, or you can bin them in the regulatory world or the analytical chemistry world, toxicological advancements, and remediation technologies. And so there are challenges across all these spaces, but they are also advancing at the same time, and they are continuously changing. And they for instance, affect one another. And an example could be the regulatory process being influenced by the number of analytes that you can test for, or EPA approved methodologies that they can identify, or what we have standards today for, or those limits of detection and the method detection limits and the method reporting limits. And as those go lower, perhaps the regulations would adjust accordingly as well. But they're all intertwined and they're all moving forward, and they make this space very challenging, yet I don't think fun's the right word, but they make it new and emerging and exciting. And here I've developed just one slide on each of those particular areas: the regulatory area, the analytical area, as well as the toxicological area, and how things are continuing to evolve. But we'll just touch briefly on them. And from a regulatory environmental compliance perspective, PFAS today are not a hazardous waste or a hazardous substance, nor are they a hazardous air pollutant. But drawing your attention to the red text, you can see that the Biden administration is currently soliciting comments for making PFAS a hazardous substance. And if that were to be implemented, that would create a pathway for potential liability for potentially responsible parties, as well as a provision for cleanup funds that could drive additional investigation, or a cleanup trigger or threshold to be established at existing sites or future sites. It also enact reportable quantities that need to be established according to state-specific cleanup levels and regulations. But that's one pathway that would, again, generate more interest and more response action with PFAS. This slide talks to some of the routes of exposure or the health effects associated with PFAS, and again, continuing to emerge, but from an exposure route, and again, drawing your text your eyes to the red text, the exposure routes, you can have defensible exposures that occur from a safety and occupational health perspective if you're a primary producer or working with these chemicals in close proximity. From a affected community perspective, it's oftentimes correlated to contaminated or polluted drinking water. And but from a larger perspective, there is a significant contribution we are finding made from atmospheric transport of these chemicals in the atmosphere to the ocean, throughout the planet. Atmospheric transport is a significant consideration that needs to be understood more, where we seem to be focusing more on the drinking water aspect or cleanup aspect. But more to follow on that. And then I just also draw your attention to the C8 health study, a 69,000 person strong effort that was done at the conclusion of the liability, the legal outcome of the Washington Works plant in Parkersburg, West Virginia, and the communities that were affected. But they found the positive correlations to those 6 conditions, adverse health effects that you see on this slide. And toxicology, using animal models, some of the limitations of that. Well, this was an epidemiological study, and it was of significant size. So I just have more confidence in studies like that for definitive adverse health effects. And then on the analytical challenges, I will walk through. At the top, we're talking about the increasing number of compounds to be identified. In 537, it was 14, then moved to 18 with 537.1, and now we're at 25 compounds, focusing on short chain compounds. Both of these methodologies are for drinking water. Red text, no published methodologies for any other matrix. So that's the state of the science today. It's difficult to look at some of the questions we have from an air sampling perspective if we don't have an agreed upon interagency, interlaboratory approved methodology. And there are defensible methods that can be used, but there isn't an agreed upon methodology, and so that makes things challenging. And then you get modified methodologies, and they're user defined. So what does user defined mean? You're not always sure. So it's slow but emerging and getting, we're already at parts per trillion, and we're getting better and better and lower limits of detection. So how is that going to affect things moving forward? An interesting question. And this slide talks about PFAS removal technologies. Generally speaking, you can group those into adsorptive, separation, and destructive technologies. The adsorptive ones are listed on this slide: granular activated carbon and single pass ion exchange resin, or regenerable ion exchange resin for that matter. Separation technologies, membranes like nanofiltration, reverse osmosis, or foam fractionation techniques. And destructive technologies are the plasmas, electrochemical oxidation, senolysis, but those technologies there's scale-up issues currently with those. There are costing issues, there are regulatory acceptance hurdles that need to be overcome. So they're not necessarily ready as mature, certainly not as mature for the market today, but they may be tomorrow, so certainly worth continuing to invest in and monitor those. But for today's conversation, we'll just be speaking about the GAC and the single pass ion exchange resin. GAC, named best available technology by the EPA. It's been around for a long time, right? There's the Sanskrit text from 2000 or from thousands of years ago that talks about storing your water in copper vessels, exposing it to sunlight, and filtering it through charcoal, activated carbon's predecessor. It's accepted in the regulatory community. Operators are familiar with it. It requires minimal maintenance. There's another bullet on this slide talks about removing other organic contaminants. So that can be a good thing or a bad thing. We've got a customer right now that has a problem with removing volatile organic compounds with their air stripper. Now they've discovered PFAS. Granular activated carbon is allowing them to remove the air stripper, and it handles the carcinogenic VOC problem and their PFAS problem. So that's a good thing. However, you can have other organics in the water that you don't necessarily want to target, but the carbon doesn't care that. And it's impacting the carbon's capacity for the target organic or the contaminant of concern. And so that would result in greater changeout, and greater frequency of changeout is going to result in increased cost. So you have to balance that. Where the ion exchange resin has a lower empty bed contact time, can have a higher flow rate therefore, which results in a smaller footprint. And if that's of particular concern to your site or your customer, or even from an aesthetic perspective, then this might be the solution for you. And you generally get a higher throughput with the ion exchange resin if the background water chemistry is situated or suited to be low in anion compounds or competing anions. But that higher throughput comes at a higher cost. Ion exchange resin generally costs more than granular activated carbon. So now you've got to do the next iteration in the calculation to understand if just the economics of the situation and increased water treated versus increased media cost. Also mentioned spent resin can be incinerated. That's the disposal mechanism, whereas the granular activated carbon can be reactivated. There can be some sustainability metrics that can be afforded to a customer that's going through a reactivation process, but there is a mechanism for the resin, and that's through incineration. But incineration costs are going up, and so that has to be considered in, again, the life cycle analysis. I see that I am in jeopardy of going over my 25-minute allocation here at slide 10, but let me just talk about the importance of performance testing to say that each water matrix, this is what I'm trying to impress upon the whole talk, is that it depends. It depends on the water quality, depends on the customer, depends upon the site constraints. And so how do you know which is the best performing media? you run a pilot. And this pilot, here's a picture of a pilot, and you can do this full scale and get greater scale up accuracy with what the full scale is going to perform like, or you can do this on an accelerated bench scale testing called the rapid small scale column test, which the scale up is harder, but you get results a lot quicker, and you're going to get a comparison between media A versus media B, and then you can do the costing calculation, and then you can take in other things into consideration, like the regulatory acceptance, as well as, footprint and items we've previously mentioned. But you do this ahead of time, and this is important to consider, so that when you operate these systems for tens and tens of years, it makes a difference when you find the most efficient or nearly the most efficient methodology. You want to find the most efficient mechanism to remove these chemicals. Additionally, I would say that it's important oftentimes to have the ability to treat water early and upfront while you do the pilot testing, while you do the rapid small scale column testing, and you can make water in the order of weeks as opposed to months or a year in order to get a $1 million plus grant or something along those lines, or regulatory approval. But if it's an emergency situation, there are capabilities and technologies that allow you to get after making clean water today for rapid response. Okay, now I'd like to share with you two case studies, one of them applying granular activated carbon and the other using ion exchange resin for removal of these chemicals from water. This first one is from Kennebunkport and Wells Water District, and this is in Maine, and were impacted with PFAS in their water. Source was identified as wastewater treatment plant sludge, as well as bioash and sludge from a paper mill. And so the municipality, based upon previous experience and familiarity with the technology, decided they wanted to go with granular activated carbon. Evoqua advised Kennebunkport to go ahead and pilot several types of carbon to determine which perform best given their, again, local water chemistry. And the results showed that a carbon made from coconut provided an additional 3 months of full-scale runtime versus the other carbons. So in the end, the Kennebunkport and Wells Water District installed a full-scale high-pressure system to remove PFAS from their water effectively. Here's some of the data that is associated with the case study and doing the pilot. Viewers right, you'll see the picture of the pilot. And then you can also see on the x-axis, I have bed volumes treated. And on the y-axis is the PFOA concentration coming in around 10 nanograms per liter. And you can see the breakthrough profile for the various carbons that were evaluated. You can see a TOC, no units listed here, but they are milligrams per liter. And again, that can negatively affect the absorptive capacity of the granular activated carbon and can affect different carbons differently. And so that's the benefit of running this particular test. And you can see the AC1230CX product hadn't broken through by 25,000 bed volumes, while the other carbons had started to exhibit breakthrough. So in the end, we came away with a single 12-foot sand vessel being incorporated up front as pre-treatment to remove any dissolved or suspended solids from contaminating or causing increased pressure differential in the granular activated carbon system, and a granular activated carbon system composed of a lead lag vessel was incorporated. And you can see the other metrics on this table, but the customer segregated react and return implementation was implemented, and you can save some significant costs, both back to the handprint footprint analogy for sustainability perspective, as well as just cost. You can react that carbon for much cheaper. You're not using virgin material. And then there are attrition losses that are associated with that, but on the order of 10 to 12 to 15%, and then you just make that up with virgin carbon, and you continue to treat water. I'll also mention that the SEPTA design is something that we offer that allows different media to be placed into the same vessels. And so if you would like to change to ion exchange resin later on here because they have to go after a particular compound that's more favorably removed by IEX, that can be accomplished. If there's a new novel adsorbent that comes to the market that is cheaper and works as good or nearly as good, but the financials indicate that that's a smart way to proceed, well, then that can be accomplished as well with the SEPTA design. And so this is just rolling the case study up, but talking about minimal impact to the ratepayers and clean water being produced, which is ultimately the end goal and objective of having safe, affordable, clean drinking water. All right, this is the final case study that I wanted to walk you through, and this is a more particularly challenging water with a total organic carbon concentration of 14 parts per million. And so the initial studies identified granular activated carbon would not be a suitable candidate for this. And because of that, then quickly moved to a comparison between different ion exchange resins at a pilot scale. And when that was done, the ion exchange resin, even with that higher concentration, was able to, although it turned black almost instantly within hours, it did work at removing PFAS. And you can see here, as demonstrated on this breakthrough chart figure here, again, throughput and bed volumes on the x-axis and in versus out concentration on the y. You can see no breakthrough after 150,000 bed volumes. So ion exchange identified as the proper media, but which ion exchange media? And so they moved to a full-scale comparison with ion exchange from different vendors and also different configurations to handle that higher TOC level. And here are the results of the full-scale comparison. This was between 4 different resins, actually between 4 different configurations. So some vendors chose, in order to handle those higher organics, to put a carbon topper on top of the resin that was handling the PFAS. Others chose 2 different resins, and Evoqua chose a singular resin, the PSR2+. And you can see the figure here. We've got our x-axis has changed to specific throughput, millions of gallons of water treated. A more accurate comparison than just bed volumes. Bed volumes is great as long as all the media volumes are the same. Here we've got different volumes of resin being used, and some have carbon and things like that. And so with those different media fills, we've got to have volume of water treated is the appropriate x-axis. And you can see after 150 million gallons of water treated, the PSR2 configuration, singular resin, had not broken through yet, but the others had. And so now you have to do the second half of the exercise, which is evaluating the cost. If the PSR2+ resin is performing 10% better but costing 25% more, well, then you might want to go with the next best alternative. But that's the next half of the consideration that needs to be considered. That sounds kind of silly, but I believe you get the concept I'm trying to push forward. So in summary, trying to understand and provide a broad portfolio of technologies and capabilities to provide a comprehensive solution. That's what's important. There's no one panacea for all PFAS removal situations, and you want to also understand and partner with someone that has the capability to do pilot testing, has the ability to get temporary mobile assets on site for treatment today or sooner rather than later, to understand some of the nuances of putting permanent solutions in and large-scale systems. But then after the fact, what are you going to do with when you need a change out? Is there a robust servicing network, and has that been demonstrated? How's the safety record of the individuals that are working with these, changing out these vessels and supplying fresh media? Is there a play for reactivation? What is the disposal know-how? And resin disposal costs keep going up, and people taking or failing to take resin. So it's a, again, dynamic situation, constantly changing. Partner with someone that has this comprehensive offering that can identify the unique solution that fits for each unique situation. Finally, action steps. This is talking towards assessing the risk at your particular site. Are they driven by regulatory requirements today that exist, or ones that are pending or that may come, or that probably are not being looked at today? There are brand concerns that need to be identified. If your brand is water, you don't want to deal with these sorts of contaminants in your finished product, regardless of what the state regulations are. So consider the risk and try to quantify it. And then if you move towards doing a more thorough sampling to understand the extent and the level of PFAS contamination, understand the analytical partner that you are working with, and the standard operating procedures that are followed and the certifications that they have. Are they going to be accepted by the regulatory community? The method detection limits versus the method reporting limits, and some of the statistical nuances of those differences. If you're going to collect the data, what are you going to do with the data? Ask that question beforehand. And then look at the remedial alternatives and try to understand the entire life cycle and what that's going to look like, not from a 1-year perspective, but a 5 or 10 or 20-year perspective. Look towards, do you want to investigate destructive technologies? If you have a smaller flow system, some of these technologies might be ready for you sooner rather than later. Or if you're going to concentrate the PFAS, how are you going to handle that? What's the ultimate disposal methods? Think through all of those particular questions and have answers, or partner with someone that can get you those appropriate answers. So in summary, we talked quickly about Evoqua Water Technologies, who we are. Water is everywhere and so are we. We talked about solutions, capabilities. Those solutions and capabilities can be grouped into adsorption, separation, and destructive technologies. And we talked just really about the adsorptive technologies and those 2 particular case studies, one granular activated carbon and the second ion exchange resin. And third, we talked about action steps and things to do or things to consider when you're partnering with somebody moving forward for identifying a PFAS treatment solution. So with that, I thank you very much for your time, effort, and energy sticking with me through this, and look forward to questions at the Q&A session. Thank you.